Okay, so far, you don't need to write this down, okay? But so far, we have the power rule, we have the product rule, we have the quotient rule, and we have trigonometric derivatives. We have 6 of them, right? Those are the rules that I have taught you so far. However, I still don't feel that we have really streamlined all of our derivatives, okay? The chain rule is a method that we can use when we have a composition function. What is a composition? Okay, like f of g of x. We have a function inside of another one, okay? The sign of x squared, all right? X squared plus 2x with quantity to the 4th power, all right? We can do most derivatives with what we have right here, but the chain rule is going to open us up to so many more possibilities. Okay? So, I would not worry about what is up here, but this is just like the precursor. G needs to be differentiable, and the composite needs to be differentiable. But then this is the rule that you need to write down. This is the chain rule. Okay, so what happens? We have the derivative of, leave the inside alone. So we take the derivative of the outside function and leave what's inside the same. But then we multiply by the derivative of what's inside. Okay? Okay? Why does it work like this? Okay? Don't write this down. I just want to show you mathematically why this is the rule. Okay? Let's say that y is f of some function u. Okay? If this is the case, then when we take the derivative, we get dy du. All right? Well, if u is some function in terms of x, then when we take its derivative, we get the derivative of u with respect to x. Well, what happens when you multiply those two together? You get dy dx. Okay? So we're taking the derivative of f, but keeping that u inside, and then we're taking the derivative of that inside function. Okay? How does that work? First example, write it down. All right, so do you notice how x squared plus 9 is inside of cosine? Okay, we have a composition function. You have to be able to recognize what a composition function is. We have a function inside of another one. So when we take the derivative, what is our outermost function? Cosine. That's what we take the derivative of first. Derivative of cosine is negative sine. But since x squared plus 9 is inside, we then, first of all, leave it alone, but then we multiply by its derivative, which is 2x. You're welcome to leave it like that. I will tell you on a multiple choice sort of situation, you will see them rearrange it to be something like this, where that polynomial is multiplied in front. The only way to get better at this is to do lots of examples. So, next one. Okay, notice how 2x is inside of our sine function. Okay. So when we take the derivative, what is our outside function? Sine. Derivative of sine is cosine. So we have the cosine of 2x, and then what will we have to multiply by? 2, because that's the derivative of the inside. When we have those trig functions with something inside, it's pretty easy to see the composition at work, right? The sine of 2x, okay? Sines are outside function, 2x is inside, okay? It gets a little bit more interesting when we move into examples like this. Okay, so first of all, square root. Have I taught you how to take a derivative of a square root? Yes, by doing what? Okay, we have to rewrite it as a 1/2 power to use the power rule. Okay, so you can see that we have a linear function inside of our square root function. So the first thing we have to do, our outermost function is something raised to the 1/2 power, right? So our derivative, we're going to use the power rule. How do you do the power rule? What do we do with the 1/2? Bring it out in front. And what happens to our power? Subtract 1. Then we have to look at the inside. 5 minus 3x. What is that derivative? -3. Sorry, don't know why I wrote 2. Okay, so I would probably rewrite this to be -3/2. 5 minus 3x to the -1/2 power. If you want to put that negative power and put it in the denominator to force it to be positive to rewrite it, that would be fine too. We're going to get to the point where we talk about vertical tangent lines, and that would be a time where you would want that in the denominator, but we can talk more about that when the time comes. Okay, I would accept this just fine, but I guess what I'm saying is I need you to understand that this means the same thing. Okay, because that could be how it would look in like a multiple choice situation. Okay, this one is for you. Please complete this problem and then check in with your neighbor. Oh, we don't quite remember the tangent rule yet, do we? When you have your derivative, check in with your neighbor. Right, Catherine, what do you have? Okay, 2x times secant squared of x squared plus 1. Very good. Make sure when you're doing the trig derivatives that your angle stays the same. Okay, so since our angle was x squared plus 1, then when we take the derivative of tangent, it is secant squared of same angle, x squared plus 1. Okay, you're replacing that angle with whatever it already has inside of it. Okay, for those trig rules. Okay. Let's see what's next. Ah, this is what I was waiting for. Okay, what I'd like you to do is write it down, and I want you and your pod to determine what the composition is, like what function is inside of which function. I'll give you 20 seconds. Okay, so pod number 2. What's our composition? Okay, and you said you were split. So
yeah, so it's like, is it 10x or 10x squared?
okay, so the pod 2 is having kind of a dispute here. Can anybody weigh in on how they feel about it? Is everyone else disputing as well? Pod 4, what did you guys discuss?
Well, I was thinking it was sine over cosine, but I don't remember the rules for tangent squared.
Well, there's not a rule for tangent squared, which is why we're talking about it, right? We know the rule for tangent,
Yeah.
okay? But what I'm trying to get you guys to see is that it's a composition, but we need to figure out what kind of composition we're dealing with, okay? Jackson.
We said it was like x squared, but instead of having x in the middle, it was tangent x.
Okay, so tangent is inside of a squared function, is what you're saying.
Yes.
Okay, I'm going to come back to part 2. Any changes of part? Mm-hmm. Chris? You don't know? Okay. So we have, it actually is tangent inside of squared. Now, it looks kind of funny because of where the square is, okay? But you can imagine it like that if it helps, okay? With logarithms and trig functions, any exponent is going to be like connected to the letters, if that makes sense. So it's going to look kind of funny. So when we take this derivative, our first job is the outside function, which is a power rule. So we're going to have 2 tangent to the first power. And then we can multiply by the derivative of tangent, which is secant squared x. Okay? So we have 2 tangent x secant squared x. All right. Here's another one that you have seen before. Okay. Let's talk about the different ways we have approached this problem. Okay. On your very first quiz in this unit, which was what, Friday, right? Friday. What did you have to do? You had to multiply it out, and then you had to use the power rule. Okay. Well, then we talked about problems like this with the product rule, right? Where we could write that as 2x plus 4 times 2x plus 4. And instead of multiplying it out, we could just use the product rule on it. Okay? Well, now we can view it as a composition, which is going to be the easiest way to do it. Okay? We have 2x plus 4 inside of the squared function. So to find the derivative, we can overall first use the power rule. Then, since it's a composition, multiply by the derivative inside, which is 2. So our derivative is 4 times 2x plus 4, or 8x plus 16, which is what you gave me on the quiz.
Isn't x squared to be 2x?
Well,
Oh, for the
yes, the inside, yep, the inside has to stay the same. Yep. Okay. Ready for some heavy lifting? Okay. Now we need to be able to kind of apply this rule in the midst of other rules. Okay. So you see here we have a quotient. Okay. Now you could write that as x times x to the fourth plus 4 to the negative 1/2 and do a product rule. You can keep it in the denominator and do the quotient rule. It's kind of 6 one way, half a dozen the other. All right. But for now, we're just going to keep it as a quotient rule. The reason I want to do this problem is so that I can show you some of the algebra involved to simplify it. Now, I know that I have told you that I'm not super concerned about simplifying, but when we get to Unit 3, it will be necessary for us to simplify. So the sooner you can see some of the algebra, the better it'll be by the time we get to Unit 3. Okay? So let's first of all just talk about the derivative, because this is something that you could see on a quiz or test. All right? So I'm going to go ahead and write this as x to the fourth plus 4 to the 1/2 power. Okay, so our quotient rule. We take the derivative of the numerator. Ooh, that's a nice one, right? Times the denominator minus the numerator times the derivative of the denominator. Now, since we have x to the fourth plus 4 inside of the 1/2 power, we are going to have to apply the chain rule. We have a composition function. So first, just like we did before, we're going to have to apply the power rule. So the 1/2 power comes down, we decrease the power by 1, leave what's inside alone. But then since we have something inside, we have to multiply by its derivative. And then in our quotient rule, our denominator is g squared, which in this case would just be what? X to the fourth plus 4. Okay, that 1/2 power gets squared. We have it now to the first power. Okay. So let's talk about some things here. What we have is x to the fourth plus 4 to the 1/2 power minus 2x to the fourth times x to the fourth plus 4 to the negative 1/2 power, and x to the fourth plus 4 in the denominator. Okay. Now, on Friday's quiz, I am perfectly happy with you stopping here. Okay? I want you to know that. However, there will come a time where we will need to know how to simplify this down. So I'm going to go ahead and show it to you now because you can handle the algebra, but you will need it later in Unit 3. Okay? So technically, we do have a GCF in that numerator. Do you see how both terms have an x to the fourth plus 4? They're just to different powers. Okay. Like in the case of number 73, we had to set the derivative equal to 0 and basically solve for where a numerator is 0. This would not be good to do with that. So we would have to do some algebra in that case. So what I want to do is I want to factor out an x to the fourth plus 4. But this is a 1/2 power, this is a negative 1/2 power. So technically our GCF would be x to the fourth plus 4 raised to the negative 1/2 power. We can factor that out. Okay, what does that do for us? Well, if we divide it out of this to the 1/2 power, what would we have left over? X to the fourth plus 4 to what power? Remember when we multiply, we add our powers? So if we were going to work backwards, if we were to multiply these two together, we would add these two powers to get back to 1/2. Okay. And then over here we would have 2x to the fourth, and then this is what we factored out. Okay, this is why this is so helpful. All right, I know it seems to be kind of a pain in the rear right now, but look. This is x to the fourth plus 4. This is x to the fourth plus 4. Well, this has a negative exponent, which means we can bring it down to the denominator. So this denominator becomes to the 3/2 power because we can swoop that down. And then our numerator, we can combine like terms. Negative x to the fourth plus 4. And there's our simplified derivative. Now, let me reiterate that I'm perfectly happy on Friday with you right here. However, if we were to have to set this equal to 0, we would have to do those 2 extra steps and then set it equal to 0. Okay? If we needed some sort of horizontal tangent line, we would need that negative x to the fourth plus 4. Okay. All right. One more? One more. First question, is this a composition? Yep. It is a composition. What is our outermost function? To the 7th power. All right. So when we take our derivative, the first thing we're going to do is the power rule. There's our power rule. Now what do we do? Now we have a quotient inside of our 7th power. Don't make that face, Trevor. Don't make that face. We have a quotient rule. This quotient rule is nice, though. Look at how linear it is, numerator and denominator. Right? Right? Okay. It's not so painful. Okay, so let's talk about the derivative of the n side. Okay, so quotient, stop. I could have pointed multiple people out, but I just happened to be looking at Trevor when he made the face. I know he's not the only one that did. Okay. Derivative of the numerator. Everybody, what is it? 2 times the denominator minus numerator times derivative of the denominator. All over the denominator. Okay. If we were to combine like terms in the numerator, what would we get? Jackson says 13. You're saying 7? Okay, I have like 3 or 4. What? It's 13? So we have 6x plus 10 minus 6x plus 3. So we have 13. Okay, there is nothing wrong with this answer right here, but I do want you to be aware of how maybe a multiple choice answer would write it. Okay, technically, okay, well we have 7. That's good. Times 13, which is, what? What's 7 times 13? 91. Okay. We have 2x minus 1 to the 6th. But then in our denominator, we have 3x plus 5 to the 6th here, and 3x plus 5 squared here. So we could combine those to 3x plus 5 to the 8th power. Okay? Now, that's not something I'm going to make you do. I'm just telling you that that would be the multiple choice answer. Okay. All right, we are in here until 9:45. All you need is one book per table because all you have to do is look at 2 problems, but I want you to try to get 2 problems done before you leave. Yeah, that's fine. Can you turn the light on your way out?